Hi everyone, welcome to my presentation. Today I'd like to discuss the fog computing technology. My goal is to help you understand the concept of fog computing. To do this, I will go through the definition, the architecture, and the application. I think it's also important to mention the security problem that comes in, then the people behind it and the current state of fog computing, and finally I will finish with a small conclusion. I really hope that by the end of the presentation you will be able to explain independently the paradigm of fog computing. So let's start. So in recent years, the cloud computing has provided many opportunities for companies by offering their customers a range of IT services. That's explained the success of Microsoft Azure and Amazon AWS and also Google. The current pay-as-you-go model is becoming an effective alternative to owning and managing a private data center. However, the current cloud can hardly meet the needs for mobility support and localization knowledge and low latency. To solve these problems, the fog computing is introduced. So the question is, what is the fog computing? Well, the fog computing is a decentralized infrastructure that pushes the resources close to end users. While this paradigm brings three several cloud-like services such as computation and storage, the fog computing is not supposed to replace the cloud, and they can both coexist within a single network. Usually they cooperate to form a three-layer delivery model, as we can see here in this picture. It's also important to mention that the term fog computing always has been associated with Cisco because of the registered trademark Cisco Fog Computing, but however it's open to the community at large. In the next, I will explain the architecture. In general, fog nodes are geographically distributed in a specific domain and have fixed locations. The user can move and request the data from nearest fog node. And the architecture should provide low latency and real-time processing. Another important requirement is location awareness. The geo-distributed fog nodes should be able to deduce its location and track end users' devices to support mobility. Also, it should not need a significant bandwidth to transmit data. And because the fog computing is a new technology, there is a lot of proposed architectures. In our example, I used the OpenFog Consortium architecture because it became a standard in 2008. So in this architecture, there is many layers. The first layer is a security net. It includes the protection for interface. This is very important to the security of the node and the general environment. The second layer is node management. It manages and controls the lowest level nodes, and the storage is to store data generated by IoT devices and other needed data for taking decisions. And there is a specific area to compute is to satisfy the computational requirement. This part is responsible for most tasks. And there is also accelerators is to satisfy the high latency or bad performance can ruin the service and user experience. Introducing the accelerators will satisfy this requirement. And also there is the network. to facilitate the communication node to node or node to device. It's important that this layer support time-sensitive networking because many services are time-aware. And finally, there is a protocol abstraction layer. Because this is used because there is many constructors and each one has its own standard. This layer satisfies interoperability for both IoT device and fog nodes and enables them to support any device. And finally, there is the sensors. This is the part which generates data. The number of applications running in fog computing platform is growing day by day. So in this presentation, I will just mention the most important one. And I will start with the smart cities. The smart cities concept has a lot of interest for science and engineering sectors. Some IoT devices in smart cities require high computing and storage capacities and pose interoperability problems. For example, many researchers has found that a centralized approach or using the cloud computing is not efficient to manage this growing volume of terminals and its geographical specificities. Data is more relevant or secure if it is processed close to the network edge. Application in this scenario are facilitated by wireless sensors like using technology NFC deployed to measure temperature, humidity or level of various gases in building atmosphere. In this case, the information can be exchanged between all sensors in a building and can be combined to form a reliable measurements. So system components can work together to lower the temperature or open the window, for example. With the fog computing applied in this scenario, smart buildings can save energy, water, and a lot of other resources. And we are going to see an example in real life. So in this example, the researchers at Ghent University in Belgium have installed air quality sensors in the roof of delivery vehicles used by Belgian Postal Service to alert citizens in real time. In a traditional approach, all data samples from the sensor are transported to centralized platform like the cloud, but here the researchers chose to perform all anomaly operation in a layer near to the sensor, which is the fog computing, and they got an impressive results. Another application of fog computing is traffic control. So the main objective of implementing it in this domain is to accident prevention, to maintaining the flow, the traffic flow, and most importantly, the recovery of relevant data to evaluate and improve the system. We can imagine that the traffic control interact locally with several sensors to detect the presence of cyclists and pedestrians, as well as to estimation and to approach speed and to distance of vehicles. This information can be used to prevent accident by sending warning signals as the cyclists approach the vehicle, for example. We can also imagine a scenario where cameras can detect the presence of an ambulance flash and automatically change the light to allow the emergency vehicle to pass. This will help to save many lives. surveillance systems. The cloud cannot be deployed for the new 4K cameras, for example, because of the viability and cost. A single high-definition camera can generate 1 terabyte of data per day, as we can see here in this picture. And the second problem is that the current monitoring systems come from different sources and manufacturers with different standards, which make them incompatible. And finally, as we all know, that cameras generate data that must be analyzed in real time, which the cloud cannot do. So to solve these problems, the solution is to propose to add a new layer, a fog computing layer for the audio and the video analysis, and also to identify the threats. This will help to manage the workload and make the migration process very easier and more efficient. For security problems, like any technology, the fog computing has many weaknesses. One of them is the man-in-the-middle attack. This type of attack is where someone, an outsider, intercepts the communication between the two sides. This attack consumes very few resources in IoT devices. So, I mean, negligible CPU consumption and memory usage. Therefore, the traditional anomaly detection method can hardly expose the attack, which make it very, very dangerous for the environment in the fog computing. Another thing is that I didn't mention is that many observers argue that authentication is the main problem in the fog computing. They argue that the traditional authentication based in the public key infrastructure is not efficient and has low scalability. So this is for the security problems. In this presentation, I briefly introduced the new paradigm of fog computing, and I have talked about its architecture and explained the reasons of the shift of using cloud computing in the growing field of IoT. And I really hope that you really learned something from this presentation I have made. Thank you for listening.